Okay, great. Thanks for having me. So I get to start off the session of guys that have last names that start with G. That was a great theme that you picked up there. The sessions have been really amazing so far, and I'm really excited to see this dialogue between different fields on this issue, and also to catch up with many of you who I haven't seen for a while because of the pandemic. So it's been great. So today I'd like to talk about active causal learning, a topic that Allison set up really nicely in her talk. The work and ideas I'm going to tell you about today were done with many different collaborators, but perhaps most centrally Anna Conan, Neil Bramley, and Azura Ruggieri. So the question I'm kind of interested in this work is like how we're so good at figuring out something by tinkering with it. And the question is important because such behaviors are so pervasive and maybe even like necessary throughout our lives. And a large part of the reason that we tinker with the world is to help us unravel the causal structure that underlies it. We do it both intuitively, perhaps most evidenced by the way that young children do it and the work that Allison was talking about, but also as adults, a large part of our formal schooling, as well as our problem solving in our everyday life, involve trying to understand causal structures. Like, so, you wake up at this hotel and there's all these light switches and you're trying to figure out which ones will actually turn the lights on, or what foods we eat that seem to cause adverse reactions and so forth. And I think understanding these processes in humans is itself an interesting cognitive question, even on its own, with some broad implications for things like education, development, meta-science, philosophy, and so forth. But also the way that my lab and others have addressed this is a good example maybe of this interdisciplinary potential of contact between people working in areas that study causality, both from philosophy, machine learning, statistics, with those in psychology and cognitive science. So although we don't have a complete theory of like how people tinker in order to learn, we do have several normative kind of candidates for thinking about this problem. And one framework in particular that's been very influential is the idea of like optimal experiment design. The core kind of metaphor or hypothesis that underlies this idea is that like people are kind of like intuitive scientists in their information-seeking actions are like optimally designed experiments in order to test maybe abstract hypotheses or beliefs that they have about the world. This general framework sort of has roots in ideas and statistics on actual optimal experiment design, where statisticians were interested in trying to give recommendations to scientists on how to optimally design experiments in order to test between relevant hypotheses and come up with formal frameworks for determining and measuring the information value of an experiment. Optimal experiment design as a framework doesn't really represent just like one particular cognitive model or anything, but really a family of kind of proposed solutions to a problem that have sort of similar structure. As one example that most people might be familiar with is like expected information gain, which sort of assigns like a utility to potential actions that one might take in the world. Think of things like flipping a switch or gathering some piece of information or wiggling something and we measure that utility in terms of the expected reduction in uncertainty over a set of like hypotheses that the learner might have given some potential outcomes. There's nothing intrinsically causal about that what I just said, but in causal situations, we can think of these hypotheses as being something like causal Bayesian graphs, and then to properly do inference in this setting, we have to account for the fact that our interventions have sort of effects on the causal structure of the world that we observe, right? And from that, we can draw, particularly from Pearl's concept of like the do calculus, which performs a type of graph surgery, right, on these causal graphs in order to account for the fact that our actions sort of sever the downstream causal forces on the variables that we actually assume to set to a particular value. Now, there's many uses of this framework in psychology. For example, in normative work, you could kind of ask the question, like, do people choose in some optimal way? But the work I'm going to talk about uses it maybe a little bit differently. So I kind of think of it a little bit like using it as a yardstick for measuring human behavior in otherwise open-ended and kind of unconstrained tasks, and then using it to help us understand how people actually perform these tests. Yeah, that's the graph. So, okay, so in particular, I'll tell you about two lines of work, one slightly older and then one slightly newer, that reflect on two principles of learning through active learning that are actually interesting to us, partly because they're really central to ideas in STEM education about, in the sense that they're like referenced repeatedly in STEM national education standards and stuff like that. The first is that people should, when trying to learn to like, collect evidence to test the belief or something like that, that they should try to come up with alternative ways the world could be, and then try to test between those different alternatives, kind of like what Rich was talking about, and the difficulty that people have with doing that is partly why it's reflected in the national standards for education. And the second one is that if you manipulate something, it's important to control other things. So onto the first one. So we did this project a while back, like looking at like how people would learn to perform interventions in order to like uncover the causal structure of a very simple system. The system that we chose was like a hypothetical microchip. So it's like a little microchip that's here on the left. It had these little components that are the little colored discs on it that you could intervene with by setting their values and turning them on or off. And what we told the people, the cover story was that there was like a chip factory that makes lots of different chips, and there was an explosion. They all got mixed together. And so your job was like to test the chips to figure out what kind of chip it was, and to help the people sort it out. And you needed to do that. You needed to design what test you needed to perform in order to determine what kind of chip it is. So I'll just go jump right into the exact experiment. This is Anna, the person who ran the experiment, but you can imagine a participant like Anna looking at the experiment. The experiment started off by showing people two possible wiring diagrams of the chip. So these are like hypothetical ways that things could be wired up. And then they click next, those kind of shrink away to de-emphasize them, and then they're presented with the real chip. And they get to decide to like turn a node on, and then the other values will update immediately after that to set to their new values depending on some causal structure. And they can continue to make interventions, as many as they like. Each time they're paying a little bit of money that they could potentially earn, so they're kind of encouraged to be efficient in doing that. And then they're asked to indicate after they've observed the number of interventions, what chip they think, which chip type they think it is, and then to rate their confidence. So we had a bunch of people do it on mechanical Turk. They were given the wiring diagrams at the top to be really explicit about the structure of the hypotheses that they were supposed to be testing between. They interviewed by clicking on things. They're incentivized to be efficient with the money costs. The network dynamics so that there's no background causes, and the probability of an effect given an active cause, meaning there's an edge between a particular node, was 0.8. And there was 27 different problem types that people were presented with that were pairs of these different examples, and lots of different ways of working. I won't go into details of that. So mostly actually people are pretty good at this. So like their structure identification is pretty accurate. Like they're about 87% correct. After like kind of performing several interventions like this, they can determine which of the set of wiring diagrams it actually is. And they're also relatively frugal with their interventions. Like most people just take one click in order to like determine what it is that they think is the correct test. So the data that we're interested in modeling though is like what decisions did they make? Like which nodes did they particularly choose to click on? That's the data of interest. And so there's several things that you can imagine that people might be trying to like sort of optimize in this case. Like one is to be efficient to gain actual information that would help them resolve which of the two chips it actually is, as well as to be effective, like so maybe it would work well no matter what task. They may kind of rely on something that's just generally good. So one version of this task that's been one model that you could think of that's like this is the expected information gain theory that I was describing earlier of this OED type, which is to say that like you choose an intervention in such a way that it will reduce your uncertainty about which of the structures is actually correct, and you can kind of formalize that as like bits of information reduced from the seam from like measuring it that way. And so in this case, it's kind of like really actually comparing the hypotheses. So it kind of compares the two and kind of says like, what's the relative evidence from one that I would gain for one or the other, depending on which thing I click on, and you sort of weigh them and try to figure out on average which intervention you could take that would make the most information. Another strategy, which we sort of actually determined sort of backwards from the data a little bit, was that like, because we saw deviations from the information gain model, was that people would have like something like we kind of described as a positive testing strategy, which is where they sort of like they pick one hypothesis and they kind of try to test that one essentially by trying to make it go like that, basically. So they sort of like choose this one, and the way they want to verify that it works, like I think it works this way, so they want to see whether it's correct that way. One way we got thinking about trying to measure these two different strategies is kind of a Bayesian estimation model where it sort of like tries to infer the relative weighting of these two strategies. So the idea admitting that people might use a little bit of both at different times, but that you could then like recover from a population or for an individual a parameter that's that measures sort of the relative utilization of these two strategies in any particular person's choice. So long story short, people fall upon a continuum, and this theta parameter, which is the one that measures like the relative balance of information gain versus positive testing strategy. There's like maximum likelihood fits. That parameter tends to relate with longer reaction time. So the more information gainy they seem to be, the longer they seem to be taking on trials. And it also leads to them being better at the task, actually. So their choices, the downstream like structure detection tasks, they do better when they make the correct choice. I won't mention about that right now, but so then we got kind of interested in like, okay, so there's like this default setting that people have that's sort of like this is the relative balance of those two things. We're interested in like, what are the set of factors that might influence the relative utilization of these strategies? And so we came up with an idea that like, you know, in the haphazardly selected set of graphs that we initially constructed, it actually turns out that if you use the positive testing strategy, you would identify the correct structure quite frequently. And so it seemed like it would be an attractive thing. So we kind of set up in the second experiment a set of conditions where we called them like PTS minus. So they were like carefully constructed such that if you use the PTS strategy, you would actually get a confounded result. And then you would have to take one more sample in order to like actually resolve the uncertainty. So it's sort of like, and since that was tied to economic incentive in the task, it sort of penalizes you for doing this strategy that might otherwise seem like it was a default attractive strategy for people to use in the first experiment. So we just and this was designed not by paying people, but just by the structure of the task itself that made it not pay off to use a strategy that didn't more explicitly compare the two structures. So then surprisingly enough, this was the mean, this is the mean, now is the mu is the mean of the population parameter for that inferred balance between information gain and positive testing strategy for that first experiment. Now we're doing experiment 2 where there's a replication where the experiments where the two strategies were roughly economically equally good. And then the one where it's negative, people shift towards using information gain selectively. So the inferred population parameter shifts upward, showing that people adaptively adapt a strategy depending on the costs and benefits of the local task that they're applied to. And then we wanted to look at like other factors that might influence like performance in this task. And so we looked at like time pressure. So like if you have less time to decide, you might use simpler cognitive strategies, and that might push people in the direction of like more of this like positive testing strategy, assuming that positive testing strategy is computationally simpler, but it kind of seems like it might be. So they had they did the same task again, now with an hourglass that was tied to their bonus. So they sort of like, it was like fading away, and the faster they decided, the more they could keep with their bonus. What you find is compared to experiment 1 again, if they had 60 seconds, 8 seconds, or 4 seconds to complete the task, they were shifting quite strategy as they shifted across, showing, I guess, again, this kind of adaptive recruitment of testing strategies across situations. And then in some follow-up work that was published a little bit more recently, Kate Nussbaum and several other students got together and did a developmental version of this. So they looked at children at a bunch of age ranges. Once we have this kind of measurement model that worked pretty good for measuring, we decided to kind of see like how changes in the strategy use would change in a default setting where it wasn't like beneficial or non-beneficial to use the two strategies. And there's this nice developmental trend going up into late adolescence of improved utilization of this information gain strategy, basically. So, and it could be tied to, I'm not necessarily sure it's tied to like brain development. It could easily be tied to formal schooling exposure that like sort of is just helping people learn about how to more effectively test between alternative hypotheses and but so, okay, so then going on to the second one question, I want to give an interim set of summary there. Let's do it at the end. Another standard that we often try to teach in STEM education is about controlling something when you manipulate something, sometimes called the control of variables strategy. So, a classic study in science reasoning and stuff like that is like if you're trying to understand a causal system, like what are the factors that might influence the growth of a plant. That the idea is that they do a lot of experiments in educational science to try to teach children the idea of like if you want to understand this causal structure, you should try to hold everything else constant and then change one thing at a time to try to understand the individual influence of each of the individual factors. It's called the control of variable strategy. it's so strong and important in science education that it's often like part of standardized testing and so forth. It's like in a canon of essentially sophisticated scientific reasoning in children. Yeah, gold standard, teaching the principle of a fair test in which only one variable is changed from one moment to the next, while all the other variables are kept the same. What's kind of interesting if you kind of come from more from the like AI machine learning perspective is that like it's not always obvious that like testing one thing at a time is actually the best thing. So if you like look at these AI algorithms that do optimal active learning, sometimes what they actually prefer to do is like change lots of things at once. So you can imagine like a situation where you might want to change like several things at once to sort of try to figure out if there, especially if you thought there's only like one thing that's really relevant, then like changing lots of things at once would be like a much more effective strategy. Yeah, so it's more efficient than control of variables in situations where the outcome has kind of a few set of causes among the variables. So we built this box when I was on sabbatical in Berkeley. So this is my California box, made out of plywood. It's got these like little switches on it and a button and a wheel and lights and stuff like that. Inside it had a little Raspberry Pi, so it was like sort of effectively arbitrarily wired up, but it was a physical box partly because of like Alice said, we thought children wouldn't believe if we were just using an iPad game. So there's switches, a coin slot for putting in money to pay for the machine to work. And then an outcome that was the wheel would spin if you activate the switch. And people were given the same exact box, but they were given two different instructions. One is that there's one switch is broken of the set of switches on the side. Which one is it? And the other one was told one switch is working, so there's a single cause, which one is it? Yeah, so you pay some money, you can set the switches however you want, like turn them on and off. You observe the outcome, either spins or doesn't spin, repeat if you desire, and then choose another switch to point to and say, this is the one that I think is the one that's like working. It turns out like if you do that kind of optimal analysis, there actually is an interesting trade-off with that instruction manipulation. So like the average number of steps to correctly identify the structure when there's one broken, meaning 5 working. If you use the control of variable strategy, you get there in 3.5 steps. But if you test half, you kind of never actually technically will find the solution because you're changing everything all the time, right? And if like only one is broken, then and 5 are working, then like turning lots of the switches on and off is never going to get you there. But and it's flipped in the other direction where it's actually much more effective when you're trying to find out which one is broken to just try to test, or which one is working. I'm sorry, is to test one at a time, right? Because then if you test one at a time, on average, you'll get there faster than if you ever change more than one at the same time. They test it now. So the data, as it turned out, was that subjects actually adaptively recruit a strategy that either looked more like control of variables, like change one thing at a time versus change multiple things. So in the one broken condition, they're using the control of variable strategy quite frequently, changing one thing, and that's reduced significantly in the one working condition. Although there is still a little bit of lingering anchoring to the moving one thing at a time strategy, which is probably a remnant of the science instruction leading through or something. One interesting thing though is that you might think that the trade-off there was not huge, right? Because you saw the savings was about one move on average. And so like, is it really worth like thinking about this strategy trade-off whenever it's really going to save you one thing if you played the game many, many times over and over again on average, right? And so, but it turns out that the advantage for doing in the one working condition increases as the number of variables go up. So experiment 1 tended to have six variables, which you can imagine if you increase the number of switches that are potentially on the board, eventually it starts becoming like really much more effective to use the split half kind of thing. So we had to take it away from physical blocks because we couldn't make that many switches, but we put it back onto a mechanical Turk and made it look kind of the same way with a web experiment. And what we just changed was like, is the one working, one broken manipulation. Interventions were costly, but they either had 4 switches, 6 switches, 10 switches, or 20 switches on the screen at the time. And so there's more evidence of this adaptive strategy use, but some evidence of this like CV strategy continuing here. So like the CV strategy, you see the test multiple TM means test multiple at once. So the test multiple is increasing in the one working condition, and the one broken, the control of variable strategy dominates. And we can also recover like the average number in our sample population, like how many things that they have to test in order to get to the correct answer. And it recovers the optimality constraints. So like it is the case that like the strategies are actually leading to like a substantially a greater number of interventions that the subject actually have to perform in order to identify the causal structure along with the predictions from the kind of ideal observer. And then we've done a recent version of this with children, again, looking at like whether children show the same sensitivity to this like trade-off. So we call it sparse and dense. It's the same as the one working like one broken situation. And here you can see that there's an adaptive trade-off. So the younger children, like in the sparse versus dense, they like reduce the amount of test multiple that they're using. And the same is true for the slightly older kids, but there's also an effective age there. And so, yeah, so study sequence 1, people's tinkering to learning strategies change with their cognitive capacities, the amount of time they have, the reward that they get for using those particular strategies in their environment. In many cases, the real world savings for optimality might actually be small. And that's sort of what we revealed, that in a lot of cases, by default, when people came into a default kind of neutrally motivated task, they ended up using simpler cognitive strategies, which generally tend to work pretty well, actually. And it was only when we actually explicitly set the environment up and stacked the deck against them that they switched to kind of more sophisticated strategies, which suggests a really kind of sophisticated use of the deployment of these strategies that's sensitive to cognitive costs. And there were also those pronounced changes in this ability with age that I think are interesting. And then study sequence 2, we pointed out, like sort of just from this ideal observer analysis, that like controlling variables is not always the most efficient way to discover causal relationships. It really depends on the structure of the environment and the assumptions that you make about that environment in order to make that be true. People also though seem to recognize that. So like they intuitively change their strategies based on those prior expectations about the environment, like the number of causes, the number of variables, as well as their cognitive resources. And even that's true for even school-age children. They seem to recognize the affordances that are given by different settings and use different experimental strategies in those 2 cases, which is quite sophisticated, actually. Comparing human behavior to these kind of normal analyses and analyzing people's behavior in terms of these kind of causal Bayesian networks and information theoretic analyses, I think allow us to make sense of this kind of open-ended behavior that people do in their daily life. It helps us kind of measure, and we also were able to use discrepancies from those models to identify potential places where cognitive constraints are coming into like constrained performance. I think we should really, I like this stuff partly because of thinking about like, we should rethink why control of variables is the gold standard for teaching experiment design, because there's a lot of cases where it's actually not the best strategy. And so I think like recognizing the reality of the world might be relatively interesting. Now, of course, you could have maybe in the question, people can say why they still think control of variables. There's other reasons to prefer control of variables in some circumstances, but I still find this analysis interesting. And also, I hope this shows some of the potential of like the type of dialogue that we're having between different communities. So that's it. Thanks.
There are seats closer to the front and below the stand in the back.
Does control the variables yield information that's computationally simpler to use in order to update beliefs? And might that explain why people seem to?
Yeah. There's a really like I saw a paper at Cogsci this year by Sam Shea that's a little bit about that kind of interpretability of the feedback, and I think that's really one of the things that you might prefer about control of variables strategy was that like you sort of it's easier to keep track of. I mean, or test is that you can kind of keep track of like an inventory of what you've done, right? Because you sort of, if you change one thing, you can use a systematic strategy of like one thing at a time, start from top to bottom or something like that. And that can be more effective for being systematic in your thinking. And maybe that's one of the reasons that's also valued as a STEM tool, is to get systematic thinking and organized testing and so forth. And if you have multiple, it gets kind of confusing after a while when you're changing 3 things at a time across several tests to sort of integrate the information. So I can see reasons why, yeah, exactly. That's like reasons why I can see why it's still favored in some senses as an educational strategy. But in terms of pure epistemics, it's sort of like questionable whether or not it's the right thing.
So to follow up to that, if you measure not the number of steps, but the real time that's elapsed, The control valuable strategy, you get rushed through very quickly.
Yeah,
And
yeah,
it's a preferred strategy from that point.
yeah, exactly. That might be-
So you were discussing the first part kind of as this dichotomy, like there are two strategies. Seems super useful descriptively, for describing the data.
Yeah.
But on the other hand, like you could have either two completely separate algorithms you switch between, or like one algorithm with a knob, which is like, how many loops of hypotheses. Do you have any data or any way of thinking about how to distinguish that?
I don't have a way to distinguish it. I know that I worked really hard to try to make one algorithm that would explain both of them. So it was the case, like there's a lot of opportunities for, if you do traditional approximation methods, if you replace sums with samples and so forth, and like reduce capacity in your model that way, you could imagine that. And so that was certainly one of the things that we first tried, but like the PTS strategy doesn't pop out naturally out of subset approximations that we could find to the OED one. And so it was partly why we sort of, like I said, we kind of bottom up this came to that strategy and put it aside and was like, okay, this seems like it's a different attractive force that's drawing people towards it. There might be, if we step back and thought not OED way, there might have been a way to come up with a unified account of it, but yeah, we ended up kind of, we did take that thing quite seriously, and after like several months, we're like, we can't come up with a reason within OED to favor the strategy that we identified.
I was going to say same question I asked Allison earlier. Part of the advantage for active learning could be better remembering what you do rather than necessarily choosing something optimal.
Yeah.
And that's related to the question about simple models as well. They may be helpful in part because you remember better what happens and what the implications are.
Yeah, absolutely. So we've in a broader research program on active learning, we do have like work on what we sort of call like active memory and stuff like that, which is like when you choose something, do you remember it better and things like that. And there are pretty strong effects that are in that direction that show that even young children, when they choose to access a piece of information, they have better recognition memory for it than if they passively see that same information revealed by someone else and so forth. And so yeah, there are like reasons like that for sure.
Well, great. Allison is asking me about citations for that, so you should give them.
Thank you for a great talk. You've talked about, or simply you're assuming that the observers or the participants are static in their strategy. Yes. Have you looked at all of the changes in strategies, how people learn from doing tasks and shift their strategies?
Yeah, I dropped the slide at the last minute, but in the developmental study that we did, looking at the change in the PTS over from like age whatever is 10 to 20 or whatever, there was a like first half of the experiment, second half of the experiment shift towards the OED, and there is a sense in which the experiments where we sort of stack the environment against people did require learning, right? Because you wouldn't know that you were in what environment you were in until you had gone a couple trials in. So the very fact that they sort of bifurcated as a function of what we gave them clearly shows that there's something about meta learning about what strategy to apply independent of the specific problem you're faced with that's going on. So there's definitely something like that in all of the experiments that we looked at.
Good time for one more maybe while switching.
Yes.
How big is the difference when you have more than one causal?
So you mean like instead of
If you have two causes, say, then split half may not be right.
two causes? So there are in the one broken there are 5 causes. So you
I'm saying that if you have two causes instead of.
oh wait, I see 2. Yeah. I see. Yeah. We didn't look at that case, like the generalizing the analysis out to the cases where there's like several more, but yeah, it's super interesting. Okay, yeah. Neil Bramley's done some stuff on like chord type interventions that are sort of similar to that. But,